Energy in the cell. So let's look at how the cell uses energy, and let's start by looking at the two different types of energy that we find. There's kinetic energy and there's potential energy. Kinetic energy is the energy of motion. So this is the energy of anything that's moving. So if we have a moving car, it's exhibiting kinetic energy. On a molecular level, heat is considered kinetic energy. In heat, the molecules are moving. Warm molecules move faster. So heat is the measure of how fast the molecules are moving, and as such, we consider it kinetic energy. Potential energy is stored energy. And if you take physics, you'll hear a lot about balls at the top of a hill. But in biology and in chemistry, we also find potential energy in candy bars. A candy bar has stored chemical energy. In all our energy transformations, we will find that energy is never created or destroyed. And we call this the law of conservation of energy. Now, energy can be transformed. We can take the candy bar and eat it and use that energy then to pedal the bike. But there's always a trade-off, and you never create energy. The energy always has to come from somewhere. So energy transforms or transformations will increase disorder, or the fancy word for this is entropy. And some of the energy with each transformation is lost as heat. So every time you transfer energy form A to energy form B, you lose some heat and you increase disorder. The sum of all the chemical reactions in an organism are what we call metabolism. And so we've got two sets of reactions. We've got reactions that build or break down molecules, and we call these the metabolic pathways. Some reactions are exergonic. Remember that this means exit and energy. So energy is leaving the reaction. Some reactions require an input of energy, and we call these endergonic. And it means that it's entering or going into. And so energy is entering the reaction. The body couples these two reactions together. If we have a reaction that gives off energy, we can use it to drive a reaction that requires energy. Otherwise, they would not occur. Here we have it in kind of a vectorial form. If the reactants, if this is potential energy on this scale, and our reactants have this much energy, and our products have a greater amount of energy, then energy will have to be added. And this is the amount of energy that has to be added. And this would be endergonic. So if we want this reaction to go, we need to have energy added. And we can add energy by having an exergonic reaction that's linked to our endergonic reaction. So in our exergonic reactant, the reactants have this much energy, the products have this much. And so we have energy that's released. And that energy can then be used to run the endergonic reaction. ATP is used to power almost all forms of cellular work. And the way ATP works, it's involved in chemical, transport, and mechanical work. So let's look at the reaction we have here below. Adenosine is linked to 3 phosphate groups. With the addition of water, the adenosine now has only 2 phosphate groups. We have an individual phosphate and ATP is made. On the left side, we have triphosphate because we have 3 phosphate groups, just like a triangle has 3 sides. We use the word tri. On the right side of the reaction, we have an adenosine diphosphate. Di meaning 2. So ATP is regenerated by cellular respiration from ADP. Let's move up and look at this diagram. So we have energy from cellular respiration. The energy from cellular respiration is used to make ATP from the starting materials of ADP plus a phosphate group. The ATP then is used for cellular work. So the molecule can be used over and over again. The ADP, the addition of energy, gives us ATP. When the energy is used, the ADP is regenerated. And the cycle can go on over and over and over again.